Hi all, welcome to my YouTube channel, Know About Embedded System. In today's video, we're going to understand one more interesting topic that's called as tail chaining in a nested interrupts. This is also one of the interview topic, and most of the time you will get questions on this saying that what do you mean by tail chaining, why it is used and how it works. These three questions you will get in the interview. So let us start the video. Before starting the video, if you're a new viewer to my channel, kindly subscribe my YouTube channel and gain the knowledge on embedded system. Let us start the video. So guys, you already know that when we have multiple interrupts, if you know that already, when there is an interrupt, there will be a process called a stacking and unstacking. So you can see on the screen. So if there is any interrupt occurs, so there will be an stacking process. This point you can see here, there will be a stacking process, and in the end there will be unstacking process. So because of this stacking and unstacking processes in a multiple interrupts, so let us see here, we have interrupt 1 and interrupt 2. So whenever you're using a more than one interrupts, this stacking and unstacking process has to be done continuously, and this will consume more time. In order to avoid this, we're going to use the tail chaining concept. So let us dive into this topic and explore. Let us move. Tail chaining, and what do you mean by tail chaining? That part we will discuss now. So what do you mean by tail chaining? Tail chaining means it is a hardware mechanism. This is what already I have explained you. The tail chaining is a hardware mechanism based optimization in ARM and other embedded system application in order to improve the interrupt handling efficiency. Time, especially the latency, it is going to increase the latency of the interrupt. So tail chaining is used to handle this point I have already explained you. The tail chaining is used to handle the multiple and back-to-back exceptions or interrupts without time consumption, without consuming the time of storing and restoring the context. So we don't use continuously storing and restoring of your context of your processor. Okay, that is called as tail chaining, and with the help of this, we are going to increase the execution time. That means we're going to reduce the execution time so that our complete applications will be running very faster, leading to faster interrupt service routine execution and increases the energy efficiency as well. So this is why we require tail chaining in our embedded system. So how it works? Let us see how the tail chaining works. So tail chaining will work. Some 3 to 4 steps are there, very simple steps. Those are all the tail chaining in action. So this will come into picture only when we have multiple interrupts in the one is in underpending and one is in an execution stage. You can see here tail chaining will come into picture only when we have multiple interrupts. If let us assume we have 2 interrupts, if the second interrupt occurs during the execution of first interrupt handler, then the tail chaining will be employed. This is what I told. Like if there is only single interrupt, no need to worry. But if there are multiple interrupts, then our tail chaining will come into picture. Okay. So with the help of tail chaining, what is the advantage or what we are going to skip? That's called as state skipping. So instead of saving and restoring of the second interrupt, so try to understand one important thing here. This is very important thing we have to understand. The saving and storing and restoring of second interrupt and its context not required in case of our regular embedded system application, because already the context has been saved into the stack when there is an interrupt, when there is a first interrupt. Okay, so that is why what we're going to skip here, we're going to skip storing and restoring of the second interrupt context. Okay, so this will skip the saving and loading the state information, and the processor directly it will jump to the ISR. So processor will directly enters into the ISR. That is nothing but second interrupt service routine. So with the help of this, as I told already, so you can save the time. The processor effectively change this type of, if you have multiple interrupts, so what processor will do? Processor will continuously create a chain of such type of interrupts. Continuously it is going to jump to the different ISRs, and it is going to create a chain. That's why it is called as tail chain. So we do not save anything during multiple interrupts. Only first time we will store into the stack, and next time only the switching will happen from one service routine to other service routine. Okay, so this is called as tail chain or tail chaining concept. So these three steps we have to remember and we have to explain in the interview. I hope this is clear. Now, how it works. There are three scenarios in our tail chaining. One by one we will see with the diagram. So the tail chaining, let us consider here the scenario. We have again two interrupts, IRQ1 and IRQ2. IRQ is higher priority and IRQ is a lower priority. So since IRQ is a higher priority, then obviously I have to execute IRQ1 because of higher priority. So when IRQ is requested with a higher priority, even IRQ2 also will be there, but this will be under suspension, or you can say pending state, not in a suspension. IRQ will be in the pending state. IRQ2 will be in the pending state, and IRQ1 will enter into execution state. So IRQ, before starting the execution, it will perform some stacking process. It will save the context into the stack. So this is called stacking process, and processor will execute ISR1, and here you can see the beauty lies here, our tail chain. So when processor exits from the interrupt service routine, so it's supposed to take the IRQ2 and it's supposed to perform the stacking process for IRQ2 as well. But since we are applying tail chaining concept here, and because of tail chaining concept, not required any pushing or any popping the content from interrupt 1 and interrupt 2. So what the processor will do, so it will skip the pushing and popping the content of IRQ1 and 2. Directly processor will jump to the interrupt service routine 2. Directly it will jump to ISR2, and then finally upon exiting from the interrupt service number 2, it is going to perform unstacking. So this process of skipping, pushing, stacking and unstacking of interrupt 1 and 2 is called as tail chaining. So because of this tail chaining, we can save lots of time in our execution. Okay, so now let us see the explanation how we have defined. You can see so interrupt IRQ1, nothing but higher priority. Let us keep IRQ1 is a higher priority. It is going to occurs first, and it will save the context into the stack, and it will execute ISR1. But IRQ2 will not come into picture because IRQ2 is a lower priority. It will be under pending state. So when ISR1 execution is completed, and if any another interrupt, nothing but IRQ2, which is under pending or a waiting state, then what processor will do? Processor will directly switch to ISR. Processor will directly switch to ISR as soon as possible. Some of the stacking and unstacking process which is required normally will be not performed. So try to understand here. This is very important. The processor will switch directly to ISR2, so by skipping some of the stacking and unstacking process. So this is called as tail chaining, and because of this we can save lots of time for stacking and unstacking process. So this is the advantage of tail chaining. This is one concept under tail chaining. I hope this is clear. And then we have one more thing called as late arrival. So late arrival, it is again similar concept with a slight difference. Now we will have IRQ1 and IRQ, similar concept. IRQ2 is a lower priority and IRQ1 is a higher priority. But here the change is IRQ2 will occur first. You can see here the IRQ2 is occurring first, and during the stacking process of IRQ2 will occur first. IRQ2 will occur first, and after some time during the process of stacking of IRQ2, IRQ1 will occur. During the stacking process of IRQ2, IRQ1 will occur. You can see here the dotted line what you're seeing. During the process of IRQ2 stacking, IRQ1 will occur. So in this situation, what will happen? Whether ISR2 should be executed or ISR1 should be executed. According to the design or according to our embedded concepts, the higher priority interrupt should be served first, even during the stacking process. The same thing will happen here. Even the IRQ2 even occurs first. Later IRQ1 occurs also, no problem. If it is under stacking process, if IRQ2 is under stacking process, the IRQ1 will be served first because this is the highest priority. After that, the ISR1 will execute, and then there will be tail chaining concept, and after tail chaining concept, our ISR2 will execute, and finally the unstacking of your the context will be taken place. So the same thing we have kept it in the explanation here, you can see. So what will happen if the higher priority interrupt, that is IRQ1 request arrives during the stacking process of your first interrupt. So IRQ1, which is the highest priority, will be occurring during the stacking process. Okay, so in this situation, obviously I told you already, since IRQ1 is a higher priority, so since IRQ2 is an under stacking process, so obviously IRQ1 should be served first because of higher priority. So this is going to ensure the higher priority will be executed first, and after that there will be tail chain, then ISR2 execution, and then unstacking process. So this is called as tail chaining with a late arrival. Okay, so this is also one important thing. And the last one, we have pop preemption. So we have pop preemption. So here also we have to consider two scenarios or two interrupts, IRQ1 and IRQ2. So what is happening here? IRQ1 will occur and stacking will be taken place, and ISR1 will execute. So try to understand here. This is the logic here. At this point, so this is called as the unstacking process of IRQ1. So IRQ requested, processor will execute ISR, and during unstacking of IRQ1, the second interrupt will be triggered. A second interrupt will be occurred. Here you can see this is the point where the unstacking of IRQ1, and at the same time the interrupt 2 will also occur here. So what will happen in this scenario? So your unstacking has to happen, but during that, at the same time, we got one more interrupt. So in this scenario, so what the processor will do? The processor will halt the popping process or unstacking process. This is called as pop preemption. The processor has to pop the stacked content, but according to our design, so it will not perform any stacking process directly. It will jump to the ISR2, and it will keep the suspension. The unstacking process will be kept it under suspension, or you can say pending state, and processor will jump to ISR, and after execution of ISR2, the popping or unstacking process will happen. Okay, so what this process is called as stack preemption. Stack pop preemption, meaning that after completion of ISR1, it's supposed to unstack the content, but because of a second interrupt, so processor did not do any unstacking, directly it went to ISR2 by keeping or by suspending the popping process in suspension. This process is called as stack pop preemption. The same thing we kept it in here. So if interrupt arrives, you can see if an interrupt request arrives just as another interrupt exiting. So upon exiting the first interrupt at this position, if any other interrupt occurs, the unstacking sequence will be stopped, and processor will go to the ISR and it will execute the ISR2. Okay, so this is called as stack pop preemption. So by performing stack pop preemption, also we can increase the execution speed as well. So this is the third scenario of tail chaining. Okay, so I hope this video is clear. So click on the like button and subscribe to my YouTube channel.